In this video, we're asked to compute the geometric area bounded by the natural log function on the interval 1/2 to 2. And the distinction between geometric area and signed area is that area below the x-axis has to count as positive if we're talking about the geometric area. We're asked to set up the definite integrals that express the geometric area, and then we're given a really nice hint. We're told what the antiderivative of the natural log function is. So in the graph of the function, I've already put in the area elements. So thin rectangles here representing a small contribution to the total area. And the height of the rectangle in the left region, it must be a positive number if I'm going to contribute positive area. And since the natural log function is negative there, the height of that rectangle must be the negative of the natural log function. The width of that rectangle is dx as usual. And then we split our integration interval at x equals 1. That's where the natural log function crosses the x-axis and becomes positive. And so in the right-hand region, the height of each rectangle is the natural log of x because that's a positive number. And the width, again, is just dx. So I'll label the region on the left region 1 and the region on the right region 2. And then I can write down A1 is the sum of all the area contributions. Those are the dAs. Those are the areas of the rectangles. And I plug in the area of that rectangle, negative natural log x dx. And then we add all these up as x goes from 1/2 to 1. Now I pull my minus sign out in front and I use my formula for the antiderivative. That's x natural log x minus x. And I evaluate this from 1/2 to 1. And when I plug in the upper limit, the natural log of 1 is 0, so that term vanishes, but the negative 1 survives. And then I subtract what I get plugging in the lower limit, which is a 1/2 natural log 1/2 minus 1/2. And I'm going to leave it that way and simplify at the end. We'll move on to A2. That's the sum of all the area contributions to that second region. All those little rectangles, those are dA2s. And the area of each of those rectangles is the natural log x dx. And I'm going to add up all those areas as x goes from 1 to 2. I use the antiderivative formula for the natural log, x natural log x minus x. I evaluate as x goes from 1 to 2. And when I plug in the upper limit here, I get a 2 natural log 2 minus 2. Then when I plug in the lower limit, again, the natural log of 1 vanishes. So the only survivor here is when I sub in 1 for x and I get negative 1. So I have a minus negative 1 at the end there. And I have a little bit of space to clean that up. That's 2 natural log 2. And then I have a negative negative 1. So I get a negative 2 plus 1, or just a minus 1. Now we can write down the total area A. And as I write down A1, I'll go ahead and distribute the factor of negative 1 that was out in front. And I get a 1 plus 1/2 natural log 1/2 minus 1/2. Then A2 was 2 natural log 2 minus 1. And I can see that my 1's cancel. And the only surviving constant here is a negative 1/2. And then the trick to simplifying this is to recognize that 1/2 is 2 to the negative 1. So the natural log of 1/2 is really the natural log of 2 to the negative 1. And the advantage of that is that we're going to use the exponent property for logs in just a second. So that exponent of negative 1 can come out in front, and I end up with a negative 1/2 natural log 2 plus 2 natural log 2 minus 1/2. So 2 natural log 2 minus 1/2 natural log 2, that's 3/2 natural log 2. And then I have my minus 1/2. And that's my final simplified answer, and we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.